Hello everybody, Mr. G here today, and we've got a bit of a hefty lesson today. I think out of all the lessons in the Forces unit, tension is by far one of the lengthier ones because there's a lot of stuff that you have to conceptualize and understand. The arithmetic is rather straightforward, but I find individuals really have a problem with the free body diagrams and whatnot. So I would expect this to be a bit longer. At any point, I would say bail for a while, go have some food or something, come back, or you can just press on like a champion and get the whole thing done in a hurry. So I'll go nice and slow so that we get this all nice and clarified, and then we'll go from there. So first thing we'll do is define tension, and really tension occurs within a material that is being pulled or stretched. So a classic example, of course, is rope. If you have two objects tied to the rope and you pull one of the objects, what's going to happen is the other object's going to move with it, and that's going to move because of the tension in the rope. Obviously, the rope did not break. It is an internal force that acts at all points along the rope in both directions. So the thing about it is that rope that was tied between two objects, when it's pulled, not only is there tension on the part that's tied to the box that's being pulled, but it's also having tension on the other box that's being dragged along. So, and they are absolutely 100% equal. Now, this whole idea acts at all points along the rope. Again, the idea here is that we have uniform ropes. So, in pretty much every case in Physics 11, you're never going to have to deal with a rope breaking. So you can assume that it's all working towards the center of mass. So, let's look at some classic examples here. Consider two carts attached by a rope being pulled along a flat surface. Friction is negligible. So that's a big, important first thing to realize. We're going to have situations with friction, and we're going to have situations without friction. If M1 is pulled to the right by a force of 40 newtons, find the acceleration of the carts and the tension in the string connecting them. So this is the order that you have to do things if you want to find the tension. Is you have to find the acceleration of the system first, then you can find the tension in the rope. So let's label some stuff that we know. Well, the first thing we know is that there is some sort of applied force. How do we know? Because we're told. We also know that there is going to be the force of gravity and the equal but opposite normal force. Notice how I'm putting a subscript of 1 on there because it's going to change according to which mass we're dealing with. Because over here, this one's a little more massive, which means the force of gravity here is going to be a little larger, which means so is the normal force. So we have those figured out, but we're missing one important vector, and that's this idea of tension. And like we said previously, tension works from both ends, which means if we look at mass 2 here, there is a force of tension going this way because it's being dragged, but on the other end, there's also a force of tension directed towards M2. Why? Because it's attached to the block here. That's the one being dragged. There's tension on both ends. So this is a key feature. In fact, I'm going to put a big star here because what's going to change now, the only thing that can really change is friction. If we added friction, then there'd be a force opposing motion pointing to the left. And again, depending on if the objects are same or different, there may be, hint, hint, different coefficients of friction for certain objects if they're different objects. So be aware of such things. So if we want to find the accelerations of the cart, we're going to have to deal with all of these forces and deal with the force net. And then tensions, we're going to actually look at 1. So let's start with the acceleration. And we can use the net force equation for the entire system. So again, we had a force going this way, we had a tension going that way, a tension going this way, and that's it. You had your Fg2, Fn2, Fn1, and Fg1. So the net force, we'll say left or right, is just equal to what? Well, it's the force applied plus the force of tension right there. But then we have tension moving in opposite direction, so we also have to subtract tension. Notice how that one is pointing the opposite way. And something important to remember, of course, as I've pointed out time and time again, F net isn't just equal to the sum of these forces, it's also equal to mass times the acceleration. Now, when we're talking about the F net as we're dealing with it now, we're dealing with the total mass. a key feature. We're trying to find the acceleration of the system, and the system includes both masses, not just one, which means it's mass total, or m1 plus m2. Now, something else happens that's super nice. These tensions cancel out. And what we're just left with is the force applied is equal to the mass total times acceleration, which means acceleration is just equal to the force applied over m1 plus m2. And when you plug in all the values, you should end up with 4 meters per second squared. So that's the key feature there, and we'll put the nice note here. Tension cancels out of the total F net equation. Okay, and that's the key feature there. I'm going to try and throw curveballs at you, where maybe I give you the acceleration, you have to find tension. Maybe I leave out certain mass values, and you're going to have to go into these conceptual understandings and find out what the mass is. Hint, hint again. So the key feature here, though, is this right there. The fact that the tensions equal and opposite, they're going to cancel out. So as soon as you figure that out, F applied has to equal mt times A. Now, if we had friction in here, where would that go? All of a sudden it would just be F app. It'd be F app subtract force of friction, and you'll see that shortly. So there's the key right there. We have the acceleration. Because now we're going to ask, well, let's go ahead and find the tension. And the key to the tension is, let's just look at one mass. So I'm going to put a line down the middle here, and let's take a look at mass 2 first. Well, if we draw our free body diagram for the third time, we're going to have something like this. And again, vertically, the two forces cancel, which means our total net force is just equal to tension, which is equal to the mass of the object times its acceleration. Now notice that it's just mass 2. In this case, we're only focused on the one mass. We're not dealing with the system anymore. However, how the heck do we find it? Because is the acceleration different? And the answer is no. Both blocks are being accelerated at the same rate. They are part of the full system, which means this acceleration here is just the one that we calculated earlier. So now it's 6 kilograms times 4 meters per second squared, which equals 24 newtons. So that gives us the tension in the rope. Now, some of you may be saying, well, what if I didn't pick mass 2? What if I picked mass 1? Well, let's take a look. Now we have normal force because we have the force of gravity. We'll say 1. We have the force applied, and this time the force of tension pointing against motion. Now we know it's accelerated to the right, which means the winner has to be force applied. So the net force is going to be equal to the force applied subtract tension, and that's going to be equal to m1 times acceleration. Again, this block is part of the system, so it's accelerating with the system's acceleration we calculated in A. So this time now, we have to solve a little bit. So tension is equal to the force applied subtract the mass 1 times acceleration, and if we put in the values, we end up with 40 newtons subtract 4 times 4, which equals, wouldn't you know it, 24 newtons. So, not shockingly, I've told you all along that the tension is equal and opposite, and if you take a look, we got the same value regardless of which block we use. So, generally speaking, since tension acts on both masses equally, we can use either mass. So this would be the case if there was 3 masses, 4 masses. It doesn't matter how many masses. We focus on one mass. We get the tension between the 2 masses as a result. So that's the system. Find the acceleration using the total system mass, then find the tension using one of the masses. So again, this is going to work for 2 carts, but of course we could extrapolate this into many different ones. So that's the easiest kind of idea. But what if we have an Atwood machine, something like this, where there's 2 masses hung over a pulley like this? Now we have to diagram what the forces are here. Well, it's kind of hard when we're looking at this because it's bent over the pulley, and we're like, well, you know, I'm not too sure. But if we start to diagram, what do we get? Well, this is FG1, and pulling up now is going to be what? Well, that has to be tension. And we know that's the same as this tension right here. and we know that this has to be Fg2, whatever the mass 2 is. Well, it's still kind of hard to picture this idea with the diagram like this. What we like to do instead is unfold or straighten the rope, because oddly enough, what's going to happen? Well, one of these masses is going to be larger than the other. And when that's the case, what's going to happen, that larger mass is going to win, it's going to pull down, and the other mass is going to get pulled up as a result. But the pulley, as long as it's frictionless and whatnot, is irrelevant to the system. So really, we can just draw it like this. And now let's go ahead and put our forces in. Well, we have the force of gravity 2, and we have tension, and we have another tension, the same tension, and we have Fg1. So all I did was take it off the pulley, straighten it out, and we have these forces. Now again, people may say, well, what about normal force and the other force? Doesn't exist. It wasn't sitting on any sort of table, so there is no normal force in this regard. So we're stuck with this. What does that mean? Now if we write the net force equation to include all, it really depends on which mass is larger. So if mass 1 is larger than mass 2, that means Fg1 is going to be winning, and the F net is equal to Fg1 minus Fg2. But if M2 is greater than M1, our net force is going to equal Fg2 minus Fg1. So again, it depends on what the mass is. This is the general case. How can we make this more difficult? Let's throw another mass below M2. Or maybe we add a couple more masses on either side. And all of a sudden, what is it? Well, we got to deal with the system. Which force of gravity is going to win? So, in general, tension acts in both directions along the rope, so it will cancel out of the equation. You'll notice how I didn't write it in either equation. Why? Because here it would be plus T minus T, and here it would be plus T minus T. Again, equal and opposite, so you just get rid of them. Let's say we have an Atwood machine like this, where one mass is 6 kilograms, one is 4. Find the acceleration of the system and then the tension of the string. I'm going to remind you that when solving for acceleration of the whole system, we consider the total mass, but when we're finding tension, we only use one mass. So let's go ahead and calculate these out. Let's start with the acceleration. Step 1, we need to find what? Well, let's draw a free body diagram. We have this is 6 kilogram. We have a string between, and we have 4 kilogram. Perfect. All right, well, there is no up and down vectors because it's not sitting on anything, which means, what do we have? Well, we have Fg of the 4 kilogram, let's just call it 1. We have a tension, we have a tension, we have Fg2. So let's find out what Fg's are. Well, Fg2 is just equal to 6 times 9.8. Fg1 is equal to 4 times 9.8. And so these values are going to be equal to 58.8 newtons and 39.2 newtons. So not surprisingly, there's more force pulling the 6 kilogram than there is the 4, so what's going to happen is this thing's going to drop to the left. Okay, so what is our net force? Well, our net force is the winner minus the loser, and what does this have to be equal to? The total mass times the acceleration. I'll even put cis down there so you realize it's the acceleration of the system. That's what we need to solve for. So A cis is equal to Fg2 minus Fg1 divided by mass total, which equals what? Well, you put in all the values, you should get 58.8, subtract 39.2 divided by, in brackets, 6 plus 4, and what are we going to end up with? We should end up with 1.96 meters per second squared. So there we go, my friends. Like I said, it's just like the carts, except this time it's blocks hanging over a pulley, but otherwise exactly the same question. So when we get to finding the tension of the string, I want to remind you that we already know what the acceleration of the system is, That's just 1.96 meters per second squared. Okay, so how did we deal with it last time? We only looked at one block. So if we take a look at our diagram, there's our 4 kilogram, there's our 6 kilogram. I'm only going to focus on this particular block. Okay, and for what reason? There is no reason. I just feel like doing it. So this is FG2, this is FG1, tension, tension. That's it. So the net force just on the 6 kilogram block is equal to what? Well, it's equal to Fg2 minus tension, which is also equal to M2 times A cis. Remember that acceleration still applies. So now all we have to do is solve for T, and T is equal to Fg2 subtract M2A cis. And we can plug in our values now. We get 58.8 newtons, subtract our 6 kilograms times the acceleration of our system, 1.96, and we should get a value of right about 47 newtons. For those of you, again, that are like, well, why would you choose that mass? Let's pick the other one. So this was the 6 kilogram mass. What if we pick the 4 kilogram mass? Well, same idea. Now, what force is winning? Well, it's being pulled down, which means the 4 kilogram mass is being pulled up, which means tension's winning in this battle. So we end up with F net is equal to tension minus Fg1, and that has to be equal to M1 times A cis. Solving for T, T is equal to M1 A cis plus Fg1, which is just equal to 4 kilograms times 1.96 plus 39.2, which is going to give us an answer of, shockingly, 47 newtons. So, in this case, does it matter which one you use? No. Is there a benefit to using one or the other? No, not technically. Again, with the card example, I chose the mass that has only the one force, which was the tension. Obviously, when friction's involved, that's no longer the case. But again, it is a system, and it works every single time. All right. Well, let's look at a different kind. We're going to switch pens because of that. Let's say we have a mass on a frictionless table, and it's attached to a hanging mass over a frictionless pulley as shown, and we have to find all these values again. Well, it all works exactly the same. Let's go ahead and label our forces. Well, we have here Fg1. Pointing up, there's going to be a tension. Pointing this way, there's going to be a tension. It's frictionless, which means there is no other force pointing back. However, in this case, we have Fg, and we also have Fn. Now, are those forces going to matter when we start to calculate acceleration? And the answer is absolutely not. If we redraw this diagram, let's draw it like this. Wouldn't you know it? We don't like this pulley either. 6 kilogram, 8 kilogram. Now, holy cow, that other mass is larger. Why is it getting pulled? It's simple. It's frictionless. There is no problem with the actual object moving. The force of gravity caused by the 6 kilogram mass is larger than anything else because it's all frictionless anyways. We're moving to the right, which means this points this way. Our tensions are there. And we still have the force of gravity and the normal force. But I think everybody knows by now that those two forces are irrelevant. Because what's the net force? Well, this is A, by the way. Our net force is equal to Fg1 plus tension minus tension, so they all cancel. And that's just equal to mass total times the acceleration of the system. So if we solve for the acceleration of the system, we get Fg1 over mass total, and that should give us a value of 4.2 meters per second squared. So there's our acceleration of the system. And again, just like the other two examples, it doesn't matter if there's a pulley there or not, you just straighten it out and draw your free body diagram. All right, so we have our acceleration of the system. That's what we need to find our tension. Now, which block should we use in this case? Well, I'm thinking we use the 8 kilogram block, and the reason is, well, watch when we do the net force. When we do the net force, what's that equal to? Well, the only force at play is that tension, which is what we're looking for, and that's going to be equal to m1 times the acceleration of the system. So let's plug in our numbers. Our mass is 8 kilograms, and our acceleration, as we found, is 4.2 meters per second squared, and we get a tension of 34 newtons, and we're done. How does block 1 change? Well, simple. Now we actually have Fg subtract t is equal to m2 times the acceleration of the system. You just have to do that one extra algebra step. Does it matter, as we've shown again and again? Absolutely not, but hey, if we can make these questions simpler, why don't we? So the final example we're going to do, I know it's been a toughie, but we're getting there, is if the same system has a friction force of 25 newtons acting on the 8 kilogram mass, let's find all the other stuff again. So we have Fg1, we have our tension, we have the same tension, this time we have the force of friction, and we have our Fg, and of course we have our normal force. Now notice, we didn't have to calculate the force of friction, they just gave it to us. And from previous calculation, we know that the force of gravity on the 6 kilogram block is 58.8 newtons, which means that it's still going to be dragged down even with this little bit of friction. So let's go ahead and draw our free body diagram. We know it's being pulled in this new case to the right. So we have Fg1, we have tension, tension, force of friction, force of gravity, normal force. Perfect. So what's our F net in this case? Well, that's equal to the force of gravity is winning, and we have a tension, but we have it going the other way, and we have the force of friction working against us. Those cancel out. So that just equals Fg1 minus the force of friction, which is also equal to the mass total times the acceleration of the system. Now we just need to solve for a cis, and that's just equal to Fg1 minus the force of friction over the total mass. And when we do so, we should end up with 2.4 meters per second squared. Now, I'm obviously not plugging in the numbers anymore. When you do this on the calculator, I would still put brackets around the numerator. Just save yourself the hassle, just in case. Who knows? Maybe you're under stress during a test, and you panic and you make a boo-hoo. So don't do it. All right, 2.4 meters per second squared, that's the acceleration of the system. Now we need to find the tension of the rope. Now there's no better or worse block to use, so in this case, I'm going to go ahead and pick the 8 kilogram block. So our net force on the 8 kilogram block, well, that's equal to tension, subtract the force of friction, and that's going to be equal to the mass of the 8 kilogram block times the acceleration of the system. So tension is equal to the force of friction plus m2a cis. Remember, that's our a cis. So when we plug these numbers in, we're going to get 25 newtons plus 8 kilograms times 2.4, and you're going to be left with 44 newtons. And you want to bet if we use the other block, we're going to get the same thing.